Jennings. I'm a current graduate student at San Diego State University studying astronomy. If we have time later, I can go over what I study specifically, but we'll kind of gloss over it during the presentation, so you don't need to worry about it too much. But anyway, here we go. So I want to talk to you about the scale of the cosmos. I don't know if you were at Dr. Quimby's talk most recently, but he gave a talk about basically the types of telescopes we have at the Mountain Lunar Observatory, how we do observations, and I want to talk to you about what exactly we observe and why we really need telescopes to do so, because it's really crazy out there in terms of the scale. So I just wanted to go over that for you. So here's our little planet, here's the moon, and for a quick overview, oh sweet, the laser pointer works. I was at a presentation last week, and the laser pointer kept bouncing off and hitting someone in the side room. It was awful. But I'm going to start with the solar system, then I'll move to the galaxy, and then I'll go beyond. So, kind of the 3 stages of scale and what we're dealing with in astronomy. But first I want to talk about the moon. The moon is very important because we see it every day. It's really the first, I would say, quote unquote, interstellar object that we see in our lives. We see the moon, full moon at night. We also see it during the day. And it's right there all the time, thankfully. So it has what we call a very stationary, at least the face is stationary towards us. This little GIF that I have shows the orbit of the moon around us. We call this a circular orbit. If you watch some science talks, they'll say elliptical. That just is an oval. A circle is just a scrunched oval. So in case you have watching more science talks. And it shows that the moon rotates at about the same rate as its orbit. So, quick little fun fact, that's why we see the same face all the time. As you can see, the straight line coming here, that's the face. It always points towards us. And I thought that was really fun. But, again, going back to the scale. So I've scaled down the moon. Can you see the little moon dot on the far right? Looks good? Okay. And so I wanted to basically show between the Earth and the moon. The distance between the Earth and the moon is roughly 250,000 miles. I know I can say really big numbers, and it's kind of hard to okay, is that down the block? Is that across the street? Is that across the United States? So what I wanted to do was kind of give you a better scale, at least mentally in your head, as to how big things are. So that's the Voyager satellite that we sent out years and years ago. What the plan was to send it out as far as we can into space and just take pictures as it flew across everything. And so imagine we are on that satellite currently flying through space at a speed of about 40,000 miles per hour, which is very fast. So first we have Mercury. It's that itty bitty dot right there. It's actually slightly bigger than our moon, and it is the first planet in our solar system. If we were to travel at that speed of the Voyager, it would take us about 3 days to get there. Oh, my apologies, not 3 days. It takes us 3 days to get to the moon if we were traveling that fast. It takes about 88 days to get to Mercury. So we've already really increased the size and distance just to get to the first planet in our solar system. Here's Venus. It is our sister planet. It is roughly the same size as us, except it has no life, and it's also orange and red while we're blue and white. And it would take about 109 days or 3.5 months to travel to Venus from Earth, even though, weirdly enough, you'd think it'd be faster. Next we have Mars, big hot topic in space travel nowadays, although personally I prefer the moon, because it takes us about 7 months to get to Mars if we were to fly over there, whereas the moon is 3 days. I don't know about you, but I'd rather travel for 3 days over 7 months. Next we have the asteroid belt. I know we can't really see it in space, but that is really the buffer period in between the inner planets and the outer planets. Next we have Jupiter, and it would take us about 600 days to get to Jupiter, or a little over 6 months. And already, not 6 months, about 9 months. Next we have Saturn, which is the second largest planet in our solar system, and it would take us about 3 years and 2 months. So we've already gone to about 9 months to a year to 3 times that distance just to get to the next planet in our solar system. Now we have Uranus. I know kids like to joke about it, but the correct pronunciation is Uranus. And it takes about 9.5 years to get to Uranus. So we've gone from about 1 year to 3 years to 9 years. And I was practicing last night, and the phrase in my head was, the farther you go in space, the farther things get. I know that sounds blatantly obvious, but it's also intrinsically true. Things tend to increase more in size the farther you go, not what we call linearly, where you have 1, 2, 3. Instead, we have 1, 3, 9. And for example, Neptune, which is now 12 years. So we keep jumping further and further in distances.
That's going 40,000 miles an hour? So.
Yeah, that's still going 40,000 miles an hour.
How do you get that 40,000 miles an hour in a spaceship, I guess?
Yeah, I'll actually go over how we can get to those speeds a little bit later. It's actually a couple slides down, but we have ways to get that fast without using fuel, and a lot of fuel. We still use fuel. But I also, oh yeah, in case you like Pluto, Pluto's not a planet. I don't care what the naysayers say, but it's what we call a dwarf planet. It's roughly a quarter the size of the moon, and our smallest planet that we have in our system is about a little over the size of the moon. And I really like this diagram because if we were to, stick each planet side by side, we take Mercury, Venus, Mars, Jupiter, and we just set them side by side from the Earth to the moon, they all actually fit. Each planet in our solar system is able to fit between the Earth and the moon. So even though it looks really close, we can fit every single planet in our solar system between us and the moon, just to give you a sense of how big things are. And as we further and further fly on the Voyager, this is past Neptune, and I don't know if you've read Carl Sagan. I actually haven't. That's a bit of an astronomer taboo to not read Carl Sagan. I read a lot of the textbooks about it, but the Voyager looked back and took its last photo, and it's what famously he proclaimed was the pale blue dot. And this is at that roughly past the distance of Neptune, where that is Earth right there. That is what we look like at a distance at the end of our solar system. So I know I want to talk about the solar system, the galaxy, and beyond, but I also wanted to really highlight a mission that we are currently going on, which is the Artemis missions. There are 3 missions. The first is the Artemis 1. The second is Artemis 2, which should be happening, I believe, later this year. Schedules don't really exist with these things. Everything keeps getting postponed for good reason. And lastly, Artemis 3. So this is a pretty complicated diagram of the Artemis 1 mission, so I really want to focus us on just these lines that are flying around. So the Artemis 1 mission that was earlier flew around, and what it does is we do this kind of loop. I know you asked about how we get these fast in these objects. What we do is we call this a slingshot method, in where we send our objects close enough to bigger planets, moons, and we use the gravitational pull to kind of fling us around, and that we're able to increase our speed while saving money and fuel. The only downside is we don't really save time, but I'd rather save money over saving time 9 times out of 10. And so this mission sent the Orion spacecraft to get slingshot around the moon, orbit a couple times, slingshot itself back, and land in the Pacific Ocean. And what this mission did was it had a satellite fly around the moon and just collect data on its orbit. How do things look? How strong is gravity at these different points? Another little fun fact, one of my colleagues actually did her master's thesis on moon gravity. Turns out it's not the same everywhere, which is why we need to send these missions to really analyze where we're going, how we're going to do it. And we have to do these things multiple times because when things go wrong, that's kind of it. and we've already lost trillions and trillions of dollars for one specific project. Next is the Artemis 2 mission, and this will be the manned spaceflight, where we will again send them around, do one loop to slingshot us again towards the moon, and these people in the satellite will fly around the moon and just again take more data, but this time with people. And then they will fly back and again land in the Pacific Ocean. The third and final mission of the Artemis is to land on the moon sometime in 2024. Using the data we took, we will again fly and circle around, slingshot ourselves towards the moon again. This diagram is kind of confusing. I went through 5 different schematics to figure out how it goes from down to kind of this weird up look. My interpretation is we again do a little slingshot to fall down in what we call the gateway orbit. This is going to stay stationary while the astronauts actually slowly fall and land on the moon. And what this gateway does is it kind of gives us a ready to go like jump off point. And so when we collect our data on the moon, fly around and slingshot back, we will connect again with the gateway. So think of it like, you're on a skateboard and you hang on to a car that's going. We'll hang on and that gateway will again circle back and then send us back down again into the Pacific Ocean. So we should be, fingers crossed, landing on the moon within the next year, which I don't know about you, but I'm really excited for that. I haven't seen a moon landing, live. I've always, watched the videos and, JFK talking about it. But I think we should do this more. I personally want to work on the moon in the future. I think it's possible. I want more funding so we can do that because I think it'd be really fun to send a picture of the Earth to my mom. I don't know about you. I think that's a pretty great dream. But anyway, let's get back into it. I just really wanted to show you about the Artemis mission. Yeah.
So how did they figure out what location to land this time compared to the past where we landed somewhere else?
That I don't know specifically in terms of the, direct, I guess, plans in terms of where they want to land.
Okay.
I know they wanted to land somewhere slightly different, and it goes back into that weird gravity isn't the same everywhere on the moon. My guess is that they're landing somewhere that's very stable, not exactly where we planted the American flag, but hopefully somewhere different. That way we can again take more data samples, possibly, I would personally find places to, set up a base of operations in the future and just take more data. That way we know exactly what we're working with in the future. So next is the solar system. I wanted to go back into that. So this is what the solar system looks like. We have our circular orbits. This is a random space body, don't worry about it. We have these things, random objects in space that kind of fly around the sun. But as you can see, all of these orbits are very circular. We have, this is actually the Jupiter orbit. Then we have Uranus, Neptune, all flying around the sun. This is what we think of when we think of the solar, the solar system model. If you've had your children, grandkids, great-grandkids, I know I have a couple of no, I'm kidding. But we usually build these very circular models. It's flat. We call that a plane. So think of it like you have a big sheet of paper and everything is kind of just rolling around on that piece of paper. That's what we like to envision our solar system as, which it is true if we thought the sun was not moving in space. However, we are within the Milky Way, and the Milky Way is what we call a dynamic system. Everything's moving. There's give, there's take, there's push, there's pull. A lot of things are going on, and we are moving within that greater flow. So this is what we would look like if we were to watch the sun move in that greater flow. So we kind of, I think of it as like a drill, where that sun is that middle part, and we, as the planets, are swirling around within its gravitational pull in space. And so we are moving all the time. I don't know if you've heard these flat earthers saying, oh, why don't we feel the movement? Well, do you feel the movement in your car while you're going 80 miles an hour? I don't know about you, but I felt like I was seated pretty stationary while I was driving over here. Whereas I'm still hitting about, speed limit 65. And so,
That helix, it
Mhm.
creates those helix forms. Of course, it makes me think of DNA.
yeah, we could get into that afterwards, but there's a lot of I call them spooky coincidences in physics and science and space. We have a lot of circles, we have a lot of spirals, we have a lot of helixes. And I like to think that they're just very stable, things to be in. And so the universe will fall into these stable sets. And so now I wanted to direct your attention to what we call the Kuiper Belt. I know we talked about the asteroid belt a little bit earlier, but then we have what's called the Kuiper Belt, which that is Neptune, and it's just a larger body of rocks and other interstellar objects that is outside of our solar system. And we are within what is also called the Oort cloud. This is a massive, basically ball of rocks, debris, that over the billions of years of our evolution as a solar system, the sun has kind of picked up various rocks, and we now have this giant Oort cloud. And so, here's another slight diagram, because that other one kind of says, okay, we're in there, here's the Oort cloud, but it doesn't give you a sense of the scale of these massive objects. And so here's the Kuiper Belt again. This KBO acronym, not object, is called the Kuiper Belt Object Orbit. We use a lot of acronyms in astronomy. I can't remember them all. If you want to go home and just Google astronomy acronyms, there's things like Batman, Cool Guy, one of them. A lot of Star Trek references. I'm not a Trekkie, so I don't get all of them sadly, but I'm trying. We use a lot of acronyms. But this is actually the more accurate scale of the Oort cloud. Think of it like we are the tip of a pin within this massive ball of interstellar objects. When I also present at schools a lot, and so kids will ask me, oh, what's the chance of us hitting like another, they've heard of a thing called a rogue planet, so it's just a planet that has been lost from its system and kind of just moves around within a galaxy. Well, we have a lot of things in the way of these types of things. So we'd kind of have to go through what I call a force field of rocks and debris before actually hitting us. Nothing is, impossible, but they're all very unlikely. But to give you another scale of just, again, traveling at the speed of the Voyager, that 40,000 miles per hour, to get to that inner part of the Oort cloud, it would take us about 300 years. So now we've gone to Neptune, which is about 12 and a half, to the Oort cloud, which is 300. So again, we're still traveling very fast, but these things are just so massive and so vast that it just takes a lot of time to get there. Again, that's a problem that we have in science. We're trying to get there. I'm optimistic. And then to get to the outside of the Oort cloud would take 30,000 years. That is the scale of the things we are dealing with. This is, again, very massive. And if we were traveling at that 40,000 miles per hour, it would take us 300,000 years to get there. Which, I'd watch it if I could, but I don't have that kind of time. And now, let's say we have, quote unquote, left our little Oort cloud and solar system, and now we are in the Milky Way. I don't know if you saw that. I'll do it one more time. This little guy on the rocket ship, that time it took to go from the left to the right side is the speed of light from the Earth to the moon. So if you turn on a flashlight or a very powerful laser, it would take about 1.25 seconds to hit the moon. And that's how fast these things are. And I really want to emphasize that, because when we get on these larger scales, we have these, I don't know if you've probably heard them, we call it a light year. It's the time, and it's basically how long it takes light to travel 1 year. So from Earth to the moon is 1 second. Multiply that by, what was the conversion? One of my classmates was harping on me about that. I think it's, about 10 million seconds to travel 1 light year. And so think of it like 10 million Earth to moon. that is how long it takes to go 1 light year. It's gonna start getting kind of freaky. Just stay with me here because now it's just talking to more and more objects. So here is our Milky Way. I love it. I don't know if you love it, but I personally love it. We call this a spiral galaxy, and it's actually a specific type called a barred spiral galaxy. That is this little bar right here. Don't ask me how I got there. I don't study galaxies. I still don't know why it has a bar like that. I've been told it's just the later stage of evolution in it. But if you were curious as to where we are right about there in the Milky Way. And to give you a scale of just how big this is, in order for us to do one single orbit, it would take about 230 million years. And so I tried doing the math to kind of scale human history versus our rotation around in the Milky Way. Human history was, I think, or is, about 20,000 years old. And so if we were to move in the Milky Way, I really want to make a cool, oh, we were here, now we're here, that'd be awesome. However, I would have to split the Milky Way into about 1,000 little pieces and then move it once for the entire human history. So to give you a scale of just how big and how long these processes take, we would move from here to here. We haven't really moved. So that is how long these processes take, and just the scale of these things are just absolutely mind-bogglingly massive. I try not to think about it too much. Sadly, I study all of this, so I have an existential crisis once every 2 to 3 months. I think I'm dealing with it okay. And our distance from the center of the Milky Way is about 100,000 light years. So think of it at about, let's see, quick math, about 1 billion moons to go from us to the center of the Milky Way. So that's just the incredible scale of just the galaxy that we live in. And if you remember that little helix spiral movement of where we are in space, it kind of implied that we move in a straight line. That's actually not the case. We exist in a flow and kind of ebb and flow and web of the universe. And so we actually move in this weird little, I like to think of it like a wave. I know, we're right by the beach, so we kind of move in a wave-like pattern around in the Milky Way. If we were to wait that 230 million years, then, we would see it. If any of you are immortal, let me know, or, write it on my tombstone after like a few billion years. And at the center of our Milky Way is our black hole. Our black hole is absolutely amazing. We believe in astronomy that most galaxies have a supermassive black hole in the middle of them. This is what it actually looks like. This is a picture of it. Here's the black hole part. This light, for some super quick black hole physics, black holes are so massive and dense that they actually bend and reflect light around them. So this is that light that's kind of being warped around itself. The weird thing my professor told me is that you can see both the front and back of a black hole simultaneously because light is moving in both places. And it's still weird to me. It's called Sagittarius A star. I did not name it. Nomenclature gets weird in astronomy. Personally, I want to name things a little bit cooler, like the big one. I don't know about you. But this circle right here is roughly the size of the black hole. And to give you, again, the sense of scale of how massive these things are, that is the size of Mercury's orbit around the sun. So if we were to place the black hole within our own solar system, it would swallow the sun and Mercury and be it'd be a very tense relationship between the black hole and Venus. So that is just the scale of the center of our universe, which we all, a galaxy, which we all fly around currently.
So the black hole is a space, but there is a portion of space, it's not an object.
Yes. It's kind of like,
I mean, I never thought of it as being an object before, but
Mhm.
Then I think when I see the slide, I think, well, just a minute, I better start thinking, it is just this huge.
It's a
area.
space
It's like a wound that everything's spewed out of or something,
or falling into.
into.
Black holes are what we call gravitational wells. So think of it as like you have a very, very massive and deep sinkhole in the middle, and everything is slowly kind of falling into it and around it. Here's a GIF of kind of the stars that are falling around that well. And so it's so massive and just dense that it's able to fling these stars around it. That's how we're able to see these things because, again, light can't escape black holes. So we kind of have to infer by the movement around it as to where it is. Because, again, we can't see it, but because it has an effect on things around it, we can say, okay, there's something there. Here's a better one. This was done by the Keck UCLA Galactic Center group. They just look at the galactic center and do diagrams so we can see. It always starts at the end. Here we go. So we can see the movement of these stars around this object in space. And so that's how we are able to see that, okay, there's something there. There's something massive in space. And so going back to where we are, this is our stellar neighborhood. These are all our neighbors around the block. However, the closest neighbor is a little over 4 light years away. So I'd say we kind of live in the boonies of the Milky Way where we're kind of separated from everyone, and it would take us, if we were to drive, let's say, a few 100,000 years to get to our next door neighbor. But we have stars like Sirius. I don't know if you've seen the Orion constellation. Sirius is in that one. We have Bernard star, which is very important astronomically. We have Alpha Centauri, 61 Cygni, this binary system. Lalande, 21,185. And let's see, 1, 2, 3, 4, 5, 6, 7, 8. About 9 stars nearest to us in the Milky Way. And again, they're all very far. Each of them is more than 4 light years away, with the farthest being a little over 6 light years away if we were to go in a straight line. And around these stars in astronomy, we like to, what are we looking at? What are we trying to find within our own Milky Way? My roommate currently is looking at what we call exoplanets. So this star right here is called HR 8799. It's roughly 133 light years away within the Pegasus constellation. You have to Google that or get the little, Sky app on your phone. I can't point it out right now because I don't think it's actually up currently. But this was the first use of direct imaging to find 4 little orbiting bodies around this star. These smaller orbiting bodies are what we call exoplanets. And so an exoplanet is just a planet that is orbiting a star that is not our own. So this is 4 of them. And there are various ways to look at these objects. However, the one I just showed you was called direct imaging, which is very hard to do. Think of it like trying to find a grain of sand in a haystack. You have to kind of be very creative in finding it. So one method is called the transiting method. What happens is the planet coincidentally passes directly in front of the star as it faces us. I like to think of it as one of your friends was photobombing a movie that you happen to be watching. And so what we do is we measure the light from the star, and if we see a little dip right as that planet crosses, we say, okay, there's something that is going in front of that. And we can then say, okay, how frequently does it dip? That would be 1 full rotation of that object. And how deep is the dip? That would let us know how big that object is in comparison to the star. A lot of the times the dip would look like this, probably about a centimeter in my height next to my entire height. However, we have ways of dealing with that. my roommate does that, and he's looking at, oh geez, he was talking about it yesterday, I think 3,000 different star systems, and trying to find, okay, is there a little dip of a planet? And I think he's found 3 so far out of that 3,000. So again, we don't know if there are exoplanets around each and every star, but we do know that there are some, which I think is awesome. And we could then go into different types of exoplanets that we found. I really like this one. It is TOI 1452b. It's what we call a water world candidate. And I know that we think of Earth as, we think of mostly water. This planet is 100 light years away, but we call this a water world because it is, from our calculations and approximations, we think it is 30% water. So 1/3 of this planet is water. To give you a comparison, the Earth is 1% water. So we have a massive crust, and if you were to compare the scale of the Earth as this big, about a centimeter, maybe smaller than that, is water. While this planet, you have its crust, an entire third of it is water. So there are many, many crazy objects in space. This happens to be one of them. I really like water worlds because with water, there's usually life, or not usually. We think there could be the possibility for life. And that goes into current habitable worlds that we found in our Milky Way. So we have the first one. To give you a quick explanation of these numbers, 1 means most habitable. Earth is our scale because, I don't know about you, but I think we are all living currently, so hence life. Mars has a 0.66 habitable in comparison of the Earth. Next is, oh geez, I just learned this pronunciation yesterday. I think it's Glycine. I really don't like astronomical pronunciations. Every time we go into class, it turns out I'm saying it wrong, so take everything for the nomenclature, take it with a grain of salt. Glycine is the first. We have Glycine C, which is the second. And if you've noticed, the 3 of these have the same name. Glycine is the name of the star that they are orbiting, whereas the number is usually, we have a star system, and we have we have Glycine 581, and then A, B, C, D, E, F, G. Each of these letters represents a smaller object around that star. So if we were to name, the sun a different number, let's say like Astro 101, we would be Astro 101c because we are the 3rd rock from that star. So that's kind of a little insight into the nomenclature. And so how do we know if planets are habitable? We have this calculation called the habitable zone. It varies based on the size and mass and overall temperature of these stars. And basically, if you're in this red zone, it's too hot. Mercury and Venus are in this red zone. Mercury is the closest one. It is so close to the sun that its atmosphere has been completely blown off. And whichever side is facing, I think, is roughly over 200 degrees, while the opposite side is negative 30 degrees Fahrenheit, and then it slowly shifts. So obviously, not going to have life there. Well, I don't say obviously, we don't think so, because our scale and how we measure life is, can water be warm enough, and can it develop, can it freeze, can it cool, can it become steam, do you have cloud systems, so on and so forth. And that is the green area, which we call the Goldilocks zone. And when we go farther into the blue, that is the cool zone. So it's too cold to have liquid water. You would see that on, I think, Neptune, which it does rain on Neptune, but the last time I checked, I think it rains diamonds. I wouldn't want to be there if I were you. That sounds like a pretty bad time. But that is the difference between these habitable zones. So when we look at stars, we do some quick math, and we can say, okay, is it in this green zone, which is the best scenario for life to exist? And I know I haven't really talked about it, but we have these things called distance indicators in astronomy. This is how we are able to figure out the distance to different objects. So first we have what's called a Cepheid variable. A Cepheid variable is just a very young bright star that pulses like this. It's in a stage of its life where it kind of comes in and out, and it decreases and then increases in brightness. An example of that is actually our North Star. I don't know if you tried to look for it in different times of the year, but sometimes it looks dimmer than you usually thought it was. Maybe a few months ago, and some more months later, it's brighter, so you're able to easily see it more easily. That's because it increases and decreases in brightness between 2 to 100 days. That's really useful for us because that's less than a human year, which means we can measure that. And so we have math to basically, I call it spooky math, to measure this change in brightness. And we have other conversions to say, okay, this change in brightness, this is how bright it seems to be. We calculate that it should be about this bright, and that difference gives us the distance. Think of it like if you had a 100-watt light bulb. You know how bright it is, after you read the package. But let's say you put it out across the street a couple times and look at it at night. It doesn't look as bright as far as it is, but we know, okay, it's across the street. We know it changed about, maybe a difference of 3 times that in its brightness. And we can use that as a conversion to figure out distances in space. Excuse me. Cepheid variables can be seen at a maximum distance of about 65 light years. After that point, we can't really see them as well, and it's a lot harder to gauge exactly how bright they are and how far they are. That's when we move into type 1 supernovae. A type 1 supernova is a star system where we have a very, very compact object. It could be a very small black hole. It could be a neutron star, which is a very, very, very dense star. And what it does is it takes the mass from a companion star and just, kind of siphons that. And eventually it reaches a critical point where it will then explode. And during that explosion, it wipes away the entire outer shell of that companion star, leaving another smaller white dwarf in its wake. And to give you a nice picture of how bright these things are in space, this galaxy is NGC 1448, and it is about 55 million light years away. So the Cepheid variable, our North Star, maximum 65 light years. This galaxy, 55 million, so that is the massive difference in scale and distance. And this bright dot, which we could say comparably is about as bright as the center of its own galaxy, is that supernova. So we've studied these things enough to where we know that, okay, the brightness should be about here, actually. We see that it's about here, so then again, we can use that distance conversion to say, okay, it's about 55 million light years away. And next are my favorite, which are type 2 supernovae. This is what I study. It's called a core collapse supernova, and essentially as a very, very massive star reaches the quote unquote end cycle of its life being very malleable, things tend to exist after its quote unquote death, which is this explosion. It kind of implodes, then explodes on itself. And here we have the before of, I'm pretty sure this is the Pinwheel M101 galaxy, and here is the type 2 supernova. This one is 25 million light years away. So the type 1 is our best distance indicator to say, okay, these are over 50 million light years away, while type 2 supernovae are slightly shorter and they are dimmer, however, they are much more frequent. Roughly 1 in 400 stars explode, and about 50% of those explosions are these collapse in on itself and then explode outwards. So while it's not as bright, they are more frequent, and if something is more frequent, that means we get to study it a lot more. So these are the type 1 and type 2 supernovae are the longer distance indicators. We also have ways of measuring galaxy distances, but it requires a lot more complicated math that I really don't want to get into. And next is beyond our galaxy. So we've talked about all of the things I've showed you, save for the distance indicators, that just helps us know how far things are. We're within the galaxy. Exoplanets, I won't say all, that is a lie. Most exoplanets that we found are within our own galaxy. We only have 4 exoplanet candidates that are outside our own galaxy. Again, finding a exoplanet is like finding a grain of sand in a haystack. Now, let's say you want to find that grain of sand in a haystack, 3 blocks over. It's going to be a lot harder. So right now, we just look at exoplanets within our own solar system because it's our haystack. But let's go further. I forgot that was there. Okay, 1 second speed. This is our sister galaxy, the Andromeda Galaxy. If you were to go out into an observatory or during one of your star nights, you should be able to see this with your own eyes. That is how close it is. However, it will be slightly dim depending. If you can see the Milky Way in the sky, you can see the Andromeda Galaxy, with your bare eyes, which I think is really cool. But the Andromeda Galaxy is roughly 2.5 million light years away. It is our sister galaxy. We are currently on a collision course within the next, I think, 250 million years. So, I don't know about you, but I think we'll be okay. But that is just the difference in how long it takes these objects to move towards one another. And again, things are moving very slow, compared to each other in space. And here are some types of galaxies that we see in space. This will become very useful. Focus more on these two. We have the elliptical, which is just this kind of giant ball of stars and objects. We have the spiral, which M101, which I showed earlier. That's as you see, there's the lack of the bar that we saw with the Milky Way. And everything else is just called irregular. We're very, very clever when it comes to categorizing things in astronomy. So we have elliptical, spiral, irregular, weird, spin, circle. That's my way of remembering it, especially for class. And so this is the Hubble Extreme Deep Field image. This was taken with over the combination of about 2,000 images taken from the Hubble satellite. And so I want to say each little dot that we see on this is a galaxy. And so, when you look in the night sky, all these little dots, most of them are stars. These are galaxies, where each one could be, let's see, we have it like that elliptical ball here. We have it like a spiral over here. Let's see, that one kind of looks irregular. And you'll see these, which are these balls with, we call them diffraction spikes. They are stars within our own Milky Way usually. That is just, we're kind of looking at it as we're looking at the larger things. I think of it like, you're trying to take a picture of the ocean and a seagull flies in your way. It's really the photobomb of astronomy. And so you'll see these are stars. I don't see any others, which is nice. But the rest of these, we can say with most confidence, are galaxies. And so to compare that with the James Webb Space Telescope Deep Field, which I don't know if you've watched it live with, I think President Biden was watching that. I canceled all my plans to watch that. But this is the next deep field of space. I liked their analogy of if you were to hold a grain of sand on the tip of your finger, hold it out at arm's length, and then point it into the sky. That is what we are looking at in terms of just how small it is, in terms of what it is on the sky. And so, grain of sand in the sky, that's just one part of what we look at. And we already see hundreds, I would say over 100 galaxies within that grain of sand. And so you'll notice that some of these look really weird. They kind of bend in this weird circle. This is a globular cluster of galaxies. So galaxies can be pulled together, or sometimes they develop at the same rate in their own lives. And what happens is they are so massive and so strong, kind of like the black hole where it kind of bends light around it, but not to the same rate. or the same strength. So what it does is it bends light to kind of distort things around it. So these weird, I like to think of them as paintbrush swaths. These are also galaxies that the light, they are behind this globular cluster. And so the light travels and then it's bent around to us. That is how massive these things are. And again, we have another photobomb star. But again, we have a, like, I think that's elliptical, another spiral. So there are billions and billions and billions of galaxies out into space the further we go. My favorite analogy is there are more galaxies in the sky as there are grains of sand on the earth from all the beaches. And it's so much we can look at, which I get really excited because that means more things I can look at and study. And we're about out of time, but if you want to see some little more objects super quick, these are, fun things I like to look at in space. This is called an AGN, which is an active galactic nuclei. These are more centers of sometimes younger galaxies, and what we see, this is called the accretion disk, so a lot of matter is falling around. We have these jets that are just shooting out beams of light and energy into space. That's usually how we can see them, is we think of it as like a lighthouse. So as it's turning in space, we'll kind of see it. That's also what we call a pulsar, which I'll talk about a little bit later. Next, we have galaxy clusters. That's what I described earlier. Here's a better look at it. So all these little things inside of it, these are galaxies. This blue haze is what we call a halo. It's not in the biblical sense of a little circle around your head, but it's more of a surrounding matter that is around these giant clusters. And lastly, this is a pulsar. So here it is in the middle. Here's that little jet that kind of trails off into it, and these are winds. Not in the intuitive sense. It took me about a year to get what a wind was. A wind is just the expulsion of matter around it. So I like to think of it like someone smoking in their car, and so as they blow out, as they drive past, you kind of get that after effect. That's the wind of that star as it's flying in space. And this one is about 800 light years away within our own galaxy. I think it's in the Virgo constellation. Aha! There's that lighthouse of that pulsar. So as it spins around, it sends a beam of light towards us and keeps spinning. And so we can measure these changes in pulses. And there are some that will spin around themselves, I think, 1 million times a second. So that is just how crazy powerful these things are. And so we would basically see a consistent light pulse that would kind of look a little bit like static as we're looking at it. And that's about it. And thank you. Yeah.
So the picture of the Hubble and the Webb took, right? I don't understand which direction it's pointing in. So we are Earth here and everything around us. Right? So which direction is it from the start? How do you know where to look?
It's kind of freaky. We don't really know where to look. This was just, think of it like you were to go out and there's a lake. And so you're thinking, okay, I just want to take a picture of just somewhere. We just point it in any direction, take a picture. This is what we see. If we wanted to take a picture another direction, roughly, this is what we see. So this is kind of us slowly scanning just the sky, and this is what we see.
So one of the things they observed was that the galaxies which are far out are bigger in size. That's not what was predicted from the Big Bang.
Yeah.
So does that mean that Big Bang is obsolete now and we need a new theory?
Not really. What it means is that we need to adjust our own theories. The Big Bang theory is still pretty solid. I actually got to talk to the woman who led that exact observation and found those galaxies. And what they said was we now need to again, take more studies and start reevaluating the processes in math that we have. Kind of like I said, with the moon being this one, like scale of 1, and then we go 3, then we go 4, maybe it's 1, 1.5, 2. And so it's really just, we need to take more information, but it's kind of like saying, oh, we didn't think that would be there. Let's start looking at it and seeing, okay, why is that? Why is that? Do we see this everywhere? And so it's more of, oh, I have more to look at, or oh, I get more funding. That's actually the main reason of these types of things. But it doesn't make the Big Bang obsolete. I know news headlines tend to get really crazy because, that's again how you get traffic. But it's more so, oh, this is something we haven't seen or we didn't expect, so let's look into it more. But most of our theories are still pretty solid. Any other general questions or comments? I know you have one. No?
Thank you.
Okay. So, yeah, thank you.